Okay, so now regarding this biometric accuracy, um, so what we do is we collect the template for users and store it in the database, and now we have a test template for a genuine user. You generate the binary pattern of it and match it with the binary pattern of the template stored for the user in the database. Of course, there may not be a exact match, so you find what is called the Hamming distance, the number of bits that match. So that's called the matching score. So what we typically do is, because just having one match threshold score would not be sufficient. We need to generate this probability density function for the user matching scores, and then decide the threshold score based on the way the uh, curve comes out to be. So typically we get a bell-shaped curve, and then so that will tell you typically what is the average matching score that you get for a genuine user. All right. So now for another user who's trying to be an imposter of this genuine user, that user also could get, we can collect the biometric template from him and generate his profile. So of course, the imposter will have a lower matching score. So this is the high end of the matching score where you get for the genuine user. For the imposter, we get a low end, low values for the matching score. But the thing is, these two curves will intersect, so that's where we have to be very careful to determine the threshold. Okay, so if now we collect again a test template for a user, because we don't know whether the user is a genuine user or imposter when you're testing, right? So you collect the test template and come up with a matching score, one single matching score, and then this is where the threshold plays a role. So if the matching score is above the threshold, then you kind of say the user is authenticated and let him log in. Whereas if the matching score is below the threshold, we say the user cannot be authenticated. But it depends. Now, the user may be genuine or imposter, right? So if an imposter manages to kind of generate a matching score that falls in this area. So this is the profile for the imposter, right? So if the imposter manages to get a matching score that is in this area, which is above the threshold, then that is a false negative. It means he's not really registered for the system, but you're letting him to log in. On the other hand, if a genuine user managed to get matching score that falls within this area, because this is his profile, right? And his matching score falls within this area, which is now less than the threshold, you're going to prevent him from logging in, and this is a false positive. Okay. So now coming to for the different biometric systems, we can have this kind of characteristic curves that will tell you the relationship between the false positives and false negatives, because you see here, if I move this threshold to the right side, I am getting more rigorous in the sense that I will be able to reduce the number of false negatives if I move to the right side, but at the same time I am going to increase my false positives, because if I increase the threshold score value, if a genuine user is not able to score that much in his matching score, he will be prevented from logging in. Okay, so that's the drawback of increasing the threshold. You're going to increase the number of false positives. Of course, you're going to reduce the number of false negatives. If you keep a lower threshold, like if I move this to the left side, I'm going to increase the number of false negatives, because an imposter with a low matching score could still have that matching score be above the threshold, so he could log in, and but we'll be able to reduce the number of false positives, because a genuine user even with a low matching score could get in, right? So we see an inverse relationship between always the false positives and false negatives. So this is the kind of curve that you get for different biometric systems. System A is one biometric system, say fingerprint. System B is say iris, and so on, iris scan. So now it comes to like how to choose a particular threshold value, right? So if it depends on the applications. So we'll say for civilian applications, we want to give equal preference to both the negatives, false negatives, and false positives. So we will choose a point where the number of false negatives or the probability of false negatives is equal to the probability of false positives. So the corresponding point is where we will fix the threshold where the probability of false positives or the distribution, the frequency is equal to the probability of false negatives. Okay. So we'll try to be balanced for civilian applications, whereas for high security applications, we do not want any false negative. We want very minimal false negative. Okay, so that's why for high security applications, we choose them to have very few false negatives. Of course, then because of the trade-off, the false positives will be too many. Whereas for forensics applications, we go to the other extreme. We do not want, or we want very minimal false positives, so we will let more false negatives. So the reason behind this is for high security applications, we do not want any imposter to be able to get authenticated into the system. So we could increase the threshold score and make it like very difficult for any imposter to get authenticated. So that will lead us to more false positives also, because the real genuine users who cannot get that much matching score due to circumstances will also be not able to get authenticated. But we could reduce the number of false negatives. Whereas in forensics applications, this is like after the fact thing. So we do not want to spend time investigating on users who are false positives. We know they are valid users. So we want to kind of lower the threshold in such a way that all those genuine users can get in, and those suspects who really did it, right, we need to investigate further on them. So we will see that imposter can also be kind of able to meet the threshold score, and then once he is able to meet the threshold score, we can further investigate on it, because he was able to get authenticated into the system. So in this cases, we'll then have a lower threshold score where we'll have more false negatives and few false positives, so that it will enable for further investigation. Okay. Okay, so what's the difference between user authentication and message authentication? So user authentication is trying to validate the user identity using like a password or biometric or a token-based approach, whereas message authentication means trying to make sure the message came from the right user. So we'll go through typically the hashing approach and encrypting the hash value with the private key of the sender, okay, or a key that is known only to the sender and the receiver. Okay. Now, what is the difference between and also in message authentication, you try to make sure the message does not come without any corruption, right? So the message should have come. Sorry, the message should have come without any corruption. So we'll indirectly check for the integrity of the message when we do message authentication. Now, what's the difference between identification and verification in the context of biometric systems? So identification is the primary means of authenticating an user. So you just get the template of the user. We may not even know the user name, and just validate the template with all those entries in the database. So it's a one-to-many comparison where just using the template will search through the entire database and see for a particular matching. So in that case, we need to have very exact matching with the test template and the ones in the database. So the biometric identifiers we'll use for them, these purposes are going to be those which are very unique for every user, like an iris scan or retinal image or the fingerprints. Whereas verification is a secondary means of authenticating users. So we would have already authenticated them through some other authentication mechanism like a password or a token. Now we want to just make sure that it is that user. So for that, we'll just do a one-to-one comparison. So once we, in this case, we know the username and we collect his biometric template and just match with his record in the database. So this is an example for signature-based recognition, where you know that this user is submitting his template signature for verification. So we can validate whether the test template test signature matches with what is stored in the database. So here some other user may also have the same kind of biometric template as his user, but we're not going to check with that user. Like signature, I can also sign like some other person, but I'm not going to check the template with that user, just with this particular user in question. Okay, so that is the case with verification. So here we could use biometric identifiers that need not be very unique for every user. So like voice recognition or signature recognition, things like that. Now, the purpose of the etc/password file and etc/shadow files in modern systems are the password file in the modern systems doesn't store the hash value of the passwords. It typically stores the username, the group ID, user ID, and all these things. And it's used mainly for utilities like if I want to find the username of a particular file or run the ls command. As I said in class, internally the Unix system keeps track of every user using user ID. So if we launch a Unix command that tries to find out the files in a particular directory, internally there needs to be a mapping between the user ID and the owner username, who is the owner of the file. Then the system refers to the password file to find out that mapping. Now the shadow file, of course, the password file is then accessible to the public, to anyone who's having an account in the system. But the shadow file is accessible only by the root or the administrator. So that file really has all the encrypted, the hash values of the passwords. It's also used for all the password management, like how frequently you should renew your password and what's the minimum number of days before which you cannot renew your password and reset your password and things like that. So we saw the rainbow table. The rainbow table basically stores the hash values of user passwords, well-known passwords. So it's like a dictionary, basically. And using that, you can launch dictionary attacks. So if you get access to the password file, you can run through the words in the rainbow table to the hashing algorithms and see which hash values match and use a corresponding username to log in into the system. Now you can make it complicated to launch the dictionary attacks by using salting. So salting will let you to kind of the same password when you run through the hashing algorithm with two different salt values, you'll get two different hash values. So now even though you have a word in the dictionary, the hash value for that word may not match with the hash value of that word, same word stored in the password file, because if now you you would have generated the hash value in the password file based on a salt value. Okay, so you could publicly store the salt value. In that case, for every word in the dictionary or the rainbow table, you have to run through it that many times corresponding to the number of users. So if you have, say, 10 users in the system, you display the salt values of all the 10 users, then you have to run through the hashing algorithm for every word in the dictionary 10 times. On the other hand, if you do not publicly display the salt values, then for every word in the dictionary you have to run the hashing algorithm how many times? That corresponds to the size of the salt value. So if you use, say, 10-bit salt value, then you have to run through it 2 to the power 10 times. Even though there may be very only few users, the salt value could be anything in this range from 0 to 2 to the 10 minus 1. So you have to run it through that many times. So you can increase the complexity of launching the dictionary attacks by using the salt value, and by publicly displaying the salt value, you could increase the complexity to a certain extent, corresponding to the number of users or proportional to the number of users registered in the system. And by not publicly displaying the salt value, you could increase the complexity corresponding to the proportional to the size of the salt, which is in terms of the number of bits that are used for the salt value. So the maximum possible salt value. So if you use 12 bits, then 2 to the 12 is minus 1 is the maximum possible salt value. So you would have to run your salting algorithm for all those possible salt values. The hashing algorithm for all the possible salt values. Okay. Now you are given here, the next question is, you are given here, say, an entry from the password file, and you want to find the user ID. So this is going to be the user ID 182. The group ID is the next number, which is 100. So the salt value is stored as the first 2 digits in the encrypted password, or the hash value of the password. So F8 together constitute your salt value. So how do you kind of extract the actual integer corresponding to the salt value? So the way you do that, we discussed in class. Remember, the 64 characters that are allowed in the password file for the hash values. So the passwords are a period and a slash and then 0 through 9. and then you have we make sure A through C, but you have to know it's capital A or lowercase a first. Okay, so uppercase A like this. So period / 0 through 9 uppercase A through Z and then lowercase a through Z. So these are the 64 allowed characters in the for the hash passwords in the salt value in the password file. So and this corresponding mapping of the numbers 0 through 63. So we have here what F and 8. So how would I run it is so F and 8. So you see here F is somewhere here, right? So B is 39, so C is 40, D is 41, E is 42, F is 43. Then 8 is over here, so if 9 is 11, 8 should be 10, right? So we found the corresponding 6-bit values, because you remember we have each of this is 6-bit segments, right? So we can represent any of these numbers in 6 bits, so that's what we're going to do. So I'm going to represent 43 in 6 bits, which is 32, 16, and 8, 4, 2, 1. So this is my 43, 32 plus 8, 40, okay, 43. And then my 10 in 6 bits is going to be 32 is going to be a 0, 16 is a 0, 8 is a 1, 4, 2, 0. Okay, so this is 10 in binary and this is 43 in binary. And now I'm going to put these two things together. So okay, now we have to view this as a 12-bit quantity. Remember, in Unix the salt is 12 bits long, so this is going to be a salt now in 12 bits. So now we have to compute the value of this. So this is going to be 1, the weight is 1, this is weight is 2, so let's just use those bits where you have weight, so 2, and this is a 4, this is a 4, this is a 0, so this is 8, and then you have 16 for this, 32 for this, 64, okay, and then you have 128, which is this one, then 256, then 512 is a 1, then 1024 is a 0, but 2048, most significant bit, is a 1. So now we have to add up all these things. So it is 2048 plus 512 plus 128 plus 64 plus 10. So 2762 is your actual integer salt value, the 12-bit salt value. Okay. Now we went through this problem in class for this dictionary attacks. Alright, so we have a system where you have a 12-bit salt value and the number of users is 2 to the 10, and the length of your passwords is 8 characters, and the maximum and the range of values for the characters, number of the size of the character set basically 64. So you can choose any characters from this set of 64 possible characters for your password, and the size of the dictionary is 2 to the 20. Now there's a 25% chance that the user password is chosen from the dictionary. So all these are given to you. So if the salt values are publicly displayed, what is the complexity, what's the average number of attempts needed to launch a dictionary attack, And if the salt values are not publicly displayed, what is the average number of attempts needed to launch a dictionary attack? So you have to do both the cases. So if the salt values are publicly displayed in the password file, for every word in your dictionary, you are going to compute the hash values for how many times, depending on the number of users. Okay. So now there are two situations. If all passwords are stored in the dictionary, what is the average number of attempts needed? If none of the passwords are from the dictionary, because remember there's only a 25% chance. So if none of the passwords are not from the dictionary, how many attempts you have to do at the average? And then we'll take a weighted average by incorporating the probability. So if all passwords are from the dictionary, the average number of attempts needed is um, for every password you need to run it to the power 10 times, because that many users are there. And then how many words are in the dictionary? 2 to the 20. And on average you would have to search about half of them before you get a success in finding a match. So 2 to the 10 times 2 to the 20 over 2, so that is 2 to the 29. If no password is in from the dictionary, again for every word that is possible, you have to try 2 to the 10 times the number of users. And then how many words are there? You have a character set that is 64 characters long, and you have to form passwords of length 8 characters. So the number of possible passwords you can have is 64 raised to 8. Okay, so that is the number of possible passwords you can have, and on average you have to try half of the 64 raised to 8, which is 64 raised to 8 over 2. Now I can write 64 as 2 to the 6, and then this 8 as it is, so 2 to the 6, the whole thing raised to 8, and this is 2 to the 6 times 8, which is 2 to the 48 over 2. So 2 to the 10 times 2 to the 48 is 2 to the 58, divided by 2 is 2 to the 57. Now let's try to incorporate the probability. There's a 25% chance that a password can be from the dictionary. So the average number of attempts is 0.25 times 2 to the 29 plus 0.75 times 2 to the 57. So we can take 2 to the 2 to the 29 common, so that is 0.25 plus 0.75 times 2 to the 28, and this 0.25 is very negligible compared to this, so it is 2 to the 29 times 0.75 times 2 to the 28, so it is 0.75 times 2 to the 57. Now if the salt values are not publicly displayed, how would you do is, the only difference is instead of multiplying everything here by the number of users, you multiply by the number of possible salt values. So you are given that we are using a 12-bit salt value, so the number of salt values is 2 to the 12. Okay, so that's what you have to do in each of these cases. So 2 to the 12 times 2 to the 20, the number of words in dictionary, on average you search half of them, so 2 to the 20 over 2, so that is 2 to the 31, and then 2 to the 12 again for the number of possible salt values times the number of possible passwords. You have to search half of them, so then 2 to the 12 times 2 to the 48 over 2, 2 to the 59. So again do the same kind of math here, 0.25 times 2 to the 31 plus 0.75 times 2 to the 59. So now you take 2 to the 31 outside, so 0.25 plus 0.75 times 2 to the 28, and so you can neglect this term, so it's 0.75 times 2 to the 31 times 2 to the 28, so it is 0.75 times 2 to the 59 attempts. Okay. Now what's the idea behind use of Bloom filter to mitigate dictionary attacks? So we use Bloom filters to catch whether a user, when a user sets his password, we try to make sure it is not in the list of bad passwords. So we generate a hash table basically, and the hash table is filled up using the hash values. It's a binary table. So for every word in the dictionary of unacceptable passwords, we will run them through hash functions. We use k such hash functions, and the hash values are what are represented in those on the corresponding to the bit positions in the Bloom filter. So you would have like the hash value starting from 0, 1, 2 all the way to say 999. If 1000 is the number of hash values you could get, the number of possible different hash values you could get. So if some word goes to the hash function, it gets a hash value of 2, then the bit corresponding to index 2 is set to a 1. Initially everything is assumed to be a 0. Of course all the bit positions are assumed to be 0. So whenever for a particular word the hash value is generated and the corresponding bit position is set to 1. If the if for a word the hash value, the bit position corresponding to that hash value is already set to 1, we just leave it as it is. Okay. So this way, if there is a bad password, all its corresponding hash values, the bit positions, have to be set to 1, because that's the way you construct the Bloom filter. So this way we cannot have any false negatives wherein we don't miss catching any bad password. But we may end up classifying a genuine password as an invalid password because the bit positions corresponding to the hash values of a genuine password may be set to 1 by some other passwords which are from the list of unacceptable passwords. So there is possibility of false positives. Okay. Now, with regards to the impact of the number of hash functions and the size of the Bloom filter or the hash table, the number of bits you have in the hash table, the larger the number of bits you have, actually the relative size, the number of bits in the hash table divided by the number of words in the dictionary of unacceptable passwords, the larger the size of this ratio, you're going to have the chances that some entries are at least a 0, because if this ratio is smaller, which means the number of bits you're storing in a hash table is relatively smaller compared to the number of words you have in the hash in the dictionary. So for example, you have say 1000 bits here in this above case, whereas if you have 1 million words, it's likely that all these 1000 bit positions are set to be a 1, right? Will be set to a 1. So now you have a test password, then its hash values, all the corresponding bit positions will be set to 1 too. So you are likely to have more false positives, a very high false positives, if your ratio is in the lower end. Whereas if you have say 1 million words, then make it like something proportional, like 5 times the dictionary size or 10 times the dictionary size. So if it's say 10 raised to 8 times or 10 raised to 7 bits, if you have 1 million words, which is 10 to the 6 words, right? So if you have something like this, then it becomes comparable, and the ratio is greater than 1. In this case it is 10, so which means there are going to be certain bits for which the bit positions are not set to 0. So in that case, for a test password, which is a genuine password, you may not be able to find all the bits corresponding to the hash values to be set to 1. So in that case, we will have lower false positives. Similarly, with the hash functions, if you use fewer hash functions, then it is possible that the bit positions corresponding to those hash values will be set to 1. If you use several hash functions, then it is possible that there's a lower chance that all the bits corresponding to the hash values of all these different hash functions will be set to 1. So if you use several hash functions, it is possible to have fewer false positives. Now the standard password encryption algorithm for Unix, and that is also explained here, right? So you need to explain just this process, how you go through DES and all these things 25 times, and then how you really come up with a 13-character password. So you get a 64-bit ciphertext from the DES algorithm, run through it 25 times, and then you append 2 zeros. That makes it 66 bits. Then you split into 6-bit segments, so there will be 11 segments, each 6 bits. And then you try to map those ASCII map the 6-bit integer values of them to a character set, 64 character set, like a period followed by then a forward slash, and then 0 through 9, capital A through Z, and lowercase a through Z. So these are the allowable 64 characters that you can represent in your password file, and these are your possible 6-bit integer values, right? So you do a mapping. Same thing for the salt value that we did before. You get a 12-bit salt value, break it up into 2 6-bit parts, and then compute this corresponding integer value and do this mapping with this character set. Okay. Now, how does salting play a role in the DES encryption algorithm? Remember, in DES we use S boxes and P boxes to generate all the substitution permutations things. So if you use salting and use a 12-bit salt values, 2 to the 12 is 4096. So you have 4096 combinations of the p tables and s tables. Okay, so that way the same password will get a different hash value if you use different salt values. Okay, depending on which s table or p table was used. So that is answer for this. How is salting used in the Unix systems during password encryption?